for section 1.5, the rectangular coordinate system. Do you recognize this man? Well, probably not. His name is Rene Descartes. He lived from 1596 to 1650. He's a very famous philosopher and mathematician. He did many things in philosophy and mathematics, including helping us get towards the scientific method which we use today. However, in mathematics, he's famous for something known as the rectangular, or Cartesian, named after him, coordinate system. Here's how it works. We place two number lines perpendicular to each other on a grid. The number line that goes left to right, okay, is called the horizontal, or x-axis. The number line that goes vertical is called the vertical or y-axis. The points where the axes cross are called the origin. The number line divides the plane into four sections. First quadrant, second quadrant, third quadrant, fourth quadrant. Okay? And they're numbered this way. Cartesian coordinates are placed in parentheses, which are called ordered pairs. An ordered pair, xy, consists of two real numbers that describe a position on the coordinate plane. For each ordered pair, the first number, x, describes the horizontal distance from the origin. Positive numbers are to the right, negative numbers are to the left. The second number, y, describes the vertical distance to the origin. Positive numbers are up and down, and negative numbers are down. Okay? So let's take a look at how this process works. Let's take a look at this example here. So here I have a coordinate grid. We'll put the origin right here, and put the x-axis here and the y-axis here. Now, I can number these any way I want, but there's no reason not to just use this scale as 1, 2, 3, 4, 5 here. Negative 1, negative 2, negative 3, negative 4, negative 5, 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, negative 4, and negative 5. Okay, so if I want to place the point minus 1, 2, the ordered pair, on this grid, I'm going to go minus 1 on the x to right here, and up 2. So this would be where the point minus 1, 2 is, and I'll just label it right there. The point 0, 3, where's 0 on the x-axis? 0 on the x-axis is right here. Go up 3, there's the point 0, 3. The point 4, 2, go over 4 and up 2, might give you that right there. The point 0, negative 2, again, 0 on the x-axis, down 2, go right here. 3, 0 would be 3 on the x-axis, 0 on the y. 3, negative 1 would be right here. Negative 2, negative 4 might be right here. Try to make that real clear for you. There's negative 4. And negative 1, 0 might be this point right here. Now you'll notice a point in the first quadrant, like 4, 2, both the x and y coordinates are positive. In the second quadrant, the first coordinate, the x coordinate, is negative, while the second coordinate, y, is positive. In the third quadrant, both coordinates are negative. And in the fourth quadrant, the x coordinate is positive and the y coordinate is negative. If you're on the x or horizontal axis, the second coordinate or y coordinate is always 0. If you're on the vertical or y-axis, the first coordinate or the x coordinate is 0. One of the ways we use the Cartesian coordinate system is to create graphs. Graphs are very useful constructions in mathematics. Here's an example. We're going to graph the equation y equals 2x plus 1. There's going to be a 4-step process to doing this. The first step is to actually create a table. Sometimes you're given input values, like this example, but sometimes you need to create your own. When I need to create my own, I usually choose 0 and some positive numbers and some negative numbers. But let's do the computations. So 0 is my input. My output is 2 times my input plus 1, so that's 2 times 0 plus 1, which of course equals 1. That gives you the ordered pair 0, 1, x, y. For an input of 1, my output is going to be 2 times 1 plus 1, which is 3, which is going to be 1, 3. For 2, it's going to be 2 times 2 plus 1, which is going to be 5. So that's 2, 5. For negative 1, you'd be a little careful here. 2 times negative 1 plus 1. 2 times negative 1 is negative 2 plus 1 is negative 1. So that's negative 1 for x and negative 1 for y for my ordered pair. And I meant to write down negative 2 here, so let me change that. That's 2 times negative 2 plus 1. That's negative 3. So that's negative 2, negative 3. So there I have created from my table some ordered pair. Our next step in graphing is to choose a scale. These numbers were fairly small. The x values were just negative 2 to 2, and the y values were also equally small and fairly close to the origin. So it's not inconvenient to count by 1 in this case. I'll do that. So I'll label these scale over by 1. And now I'm going to graph my ordered pairs. So what were my ordered pairs? Well, if you remember, the first one was 0, 1. So I'm just going to put that one there. The next one was 1, 3. Okay, the next one was 2, 5. So I'm putting these here. The next point was actually negative 1, negative 1, which is right here. And my next point was 2, negative 3. Now you notice the inputs that I chose were all integers. But the inputs don't have to be integers. I could have chosen the input of 1/2, or say 1.785, or the square root of 17 for that matter. If I connect these dots, this gives me a graph of this equation. This graph of this equation, which I like to label y equals 2x plus 1, put an x here and a y here for my axis, and these arrows indicate this goes off in any direction. But this graph represents all possible points for any input, including strange ones, not just integers. Not everything, however, is a graph, as we'll see with this next example. So I'm going to draw a graph for x squared minus 1. Now, this time I didn't give you some inputs, so I'm going to choose inputs. I like the input 0 if I'm allowed to use it, some positive numbers, no reason to not use 1 and 2, and some negative numbers. Let's use minus 1 and minus 2. So my output is going to be the input times itself minus 1. So 0 squared minus 1 is negative 1. That gives me the ordered pair 0, negative 1. My output here is going to be my input 1 squared minus 1, which if I do the arithmetic gives me the answer 0. 2 squared minus 1 is going to be 4 minus 1, or 3. So I have 2, 3. Negative 1, you got to be a little careful. Negative 1 squared, or negative 1 times negative 1, is positive 1. Minus 1 is also 0. So just be a little careful with your arithmetic there. And negative 2 squared minus 1 is 3. That's a negative 2, 3. So let's use the same scale. So I'll label here. I notice that while I have some positive values for my y value, I don't have too many negative values, so I'll just go down to negative 1 in this case. Now let's label these points. 0, negative 1, 1, 0, 2, 3. You'll notice already that it doesn't look like this is connected by a line. Negative 1, 0, and negative 2, 3. No line here. If I connect these dots, I might get a shape that looks like this. As we'll see later in this course, this shape has a name, but it's certainly not a line. Let's talk about some more practical examples and the idea of scaling. Previous two examples, x and y, were fairly close to the origin. This is not often the case. When we decide what numbers to use for marks or labels on the axis, finding a scale is called finding a scale for the axis. When the numbers are large or small, we need to count by numbers other than 1 or 2. One way to determine an appropriate scale is to use this little formula here, highest number minus smallest number over 10. Then round to something easy. Rarely is this an easy number. Note, this is just a guideline. You actually can select any logical values you wish. Now suppose you wish to graph the following table, which has age in years and income in dollars. So for example, this says that a 30-year-old, the average income is $51,106. And for a 60-year-old, the average income is $57,386 per year. We certainly don't want to count by ones on each axis. That would be a really big graph. Using the guideline given above, we might use 10 on the horizontal axis. This looks like we're counting by tens here. And maybe 4,000 on the vertical. Now the way we got that 4,000 is using that guideline given above. If I take the high value minus the low value, that equals, let's use our calculator here just for a second, that equals 37,171. Dividing by 10 gives me 33,117.1. Well, that's not a very convenient number, so I'm going to round to something nice, maybe 4,000. But you also notice that we don't start very close to 0. The smallest number is about 28,000. So I might use a little technique to help me with that. Let me show you how I might graph this. I notice I don't have any negative x or y values, so I'm going to use my x and y axis right on the edge here. This is my y axis. This is my income. It's nice to label. And this is my x axis. And this is my age. Now, these little marks on my graph paper are awful close, so I'm not going to count by ones. I'm going to count by 2. I'm going to do 10, 20, 30, 40, 50, 60, 70, 80, so on. Okay, I think I have enough there. Now, counting this way, I might notice that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22 squares going that way. So I might use every 2 to count. Now, because I'm starting, one way to get around this is to say, look, I'm going to start at 28,000. And then I'm going to count, let's say, by 4,000. So my next one would be, what, 32,000. And then I'm going to count 36,000. And then I'm going to count, oh, let's keep going, 40, 44, 48,000, 52,000, okay, 56, 60, 64, and 68. Now, if I count this way, you'll notice that this space is much larger than this space. This right here is 4,000, and this is 28,000. To indicate that that is different, a lot of times people use this double hash mark there to indicate that that's not uniform. Now let's plot these points. 20, 31,790. Now you notice I'm not going to be able to get exactly 31,790. But if this is 20,000 and this is 30,000, 32,000, this is 30,000, so I might guess that that's maybe about right here. And at age 30, 51,106. Okay, let's go all the way up there. Again, this at age 30 is 50,000 right here, so 51,106 might be about right there. You do have to estimate. 40,000, we're going to do 62,000, and a little bit more, so maybe about right there. And 50,000, 65, I mean at age 50, 65,000. Okay, so we might say that's almost maybe about right here. And back at 60, you notice the income actually goes down a little. Some people are retired at 60, probably not making income there. So maybe about right here at age 60. And at age 70, we're down to 28,305, so maybe somewhere around right there. So there's a way to indicate that graph right there. You don't really need to connect the dots on this example. Let's do one more practical example. Let's use a verbal description to draw a graph. In the bulk foods department at a store, candy costs $2.29 per pound. Okay? I want to use a table using the inputs 0, 1, 2, 3, 4 for pounds purchases and the output the total cost of the candy. You might notice that the total cost of the candy, Y, is $2.29 per pound. Okay? And the input is, we might call X. So here I have 0, 1, 2, 3, 4, as indicated. My output, of course, if I don't buy any candy, I don't have to pay anything. My output if I buy 1 pound is $2.29. What's my output if I buy 2 pounds? That's 2 times $2.29, or $4.58. 3, $2.29 times 3 is going to be $6.87. 4 is going to be $9.16. Now, the x-axis is pretty easy to indicate here. The y-axis is not so easy. Okay? It says use your graph to estimate the total cost of 2.25 pounds of candy, or 1.75 pounds, or 0.5 pounds. Now, by using this example, this kind of indicates to me that maybe I, again, should make my x-axis here. Let me move this up just a little bit. The entire bottom of my graph. Okay, so this might be my x-axis here, my input. My input there is going to be pounds of candy, right? So I'll write that down, pounds of candy. And my output is going to be my total cost. Now, I notice my cost goes up to about $10. Okay, so how can I do that? Well, I might decide that this, I'm going to skip every 2 again. Let's see if that works. 3, 4, 5, 6, 7, 8, 9, and 10. Okay, that seemed to fit there. And my outputs are only 4, so I'm going to count by 4s here. And you'll see why that makes that a little convenient in a minute. So if I plot these points, of course, no, and I'm just going to put cost here. No, and I can put dollars, indicate what my costs are in. No candy bought, no paid. 1 pound of candy pot is about 2.29, so maybe about right there. 2 pounds of candy caught, about 4.5. Okay, 4.58. So 4.58 might be about right there. 3 pounds of candy, 6.87. It's almost 7, okay? So 4 pounds, 3 pounds of candy, 6.87, maybe about right here. And 4 pounds of candy, 9.16. 9, a little bit more. Maybe about right there. Now, if I've drawn this right, I did a pretty good job. I have something that's pretty close to a line. Okay, here, it looks like. And this is my y equals 229x. Now, use your graph to estimate the total cost of 2.25 pounds of candy. Well, if this is 2 pounds and this is 3 pounds, this is 2.25 pounds of candy. Now I'm going to take my ruler and I'm going to just draw a dot up there at 2.25. And if I go across here, you'll see that this is indicated maybe about right here. So what is that? Well, that's somewhere between 5 and 5.5. So my estimate might be at 2.25 pounds on about $5.25. Now remember, that's an estimate. That's not exact. 1.75 pounds, again, 1.75 I might have here. Looks like 1.75 pounds is just about $4. And a half a pound of candy, half a pound would be right here. Half a pound of candy looks like it's between 1 and 2. So again, I might say 1.25. Now remember, these are estimates, but I got those from the graph.